This discussion wraps up the second half of our discussion on amperometric transducers. And as we indicated earlier, we covered the first 5 parts of this lecture in which we talked about everything from measurement options to sensor design characteristics. And I think some of you may have already been very familiar with sensor design characteristics, but we included it anyway for the sense of completion. We leave now time to discuss the 3-electrode amperometric system and then the sensor output. I think I want to stress here that the 3-electrode amperometric system can be a little difficult to understand, but as a practical matter, all of the necessary electronics and aspects of the probes are integrated into modern systems. So it doesn't quite look the way some of our pictures will show, but the pictures are designed to create a better understanding of the system. In a general way, the amperometric system is a 3-electrode system. First of all, we have the working electrode, which is the platform under which the chemical reaction takes place. And we see here's the working electrode, and then this is the reaction that's taking place on the surface. The reference electrode is used to measure the solution potential. All right, so that's the reference electrode, RE, shown down here. And basically what happens is that provides a reference bias. The counter electrode, also called the auxiliary electrode, provides the means of applying input potential to the working electrode. Now this can be sort of confusing because what happens is that in a way we have the counter electrode, and what really this is going to do is through the solution provide a pathway between the counter electrode and the working electrode. So basically the way the system functions is that we control the difference between the working electrode and the reference electrode and measure the current flowing between the working electrode and the counter electrode. So we've got the control aspect of the working and the reference electrode, and then the current flow relates to the measurement that is actually of interest in terms of the concentration of the analyte. So in essence, the system controls the potential difference between the working electrode and the reference electrode at a desired potential by injecting the proper amount of current into the counter electrode. All right? Proper amount of current into the counter electrode. The counter electrode provides a mean of applying input potential to the working electrode, and the purpose of the counter electrode, as I've mentioned a couple times, is to complete the circuit and allow the charge to flow. Consequently, the counter electrode needs to be manufactured from inert material like carbon or platinum, and the size should be much larger than the working electrode to assure no current limitations arise. Having said all that, the sensor, which is composed of 3 parts, all those aspects of the sensors are integrated through this potentiostat topology. This potentiostat controls the working electrode's potential in the multi-electrode system. Right? So here's the potentiat, and we see that this really has all the aspects of the control leading to a specific voltage output. And this is where our sensor is over here with the with the reference, the working, and the control electrode, of course, is shown as part of the sensor. So the 2 major blocks determine the functions of the potentiat system. All right? The control part maintains the cell voltage at a desired potential. It forces the voltage between the working electrode and the reference electrode to be the same as the voltage bias. Right? Same as the voltage bias. The amplifying part reads out the cell current from the control electrode and converts such signal into a voltage. So you've got this over here, the control over here, and an input current, and it's amplified, and that gives you the voltage out. So in some ways it's kind of a simple system, but the role of the 3 different components of the sensor can be sort of confusing. Sometimes it helps to reread this a few times, but essentially what happens is everything is integrated into this potentiostat, which simplifies and handles all the electronic, the bias, the voltage feeds, and things like that. So really it's in some ways it's more straightforward than it appears, but it does help to understand the foundation for the 3 components of the amperometric system. Basically what happens is when you look at the control, the reference, and the working, you see the electrolyte is what sits sits in there and it links the counter electrode and the working electrode. So what happens is, again, as I've mentioned, it's not always intuitively obvious, but it's the bulk solution that provides the connectivity between and the interaction between the counter electrode and the working electrode. So what happens is you've got certainly gradients at the surface, then gradients across the bulk solution, and again gradients that occur in proximity to the working electrode. And what ends up happening is that you've got this fundamental difference between the shown here as EA between these different portions of the gradients. And of course this is what's really going to be used to measure some of the output. So basically, having said all that, the sensor output is sort of dictated by the Cottrell equation. And so amperometric sensors employ a voltage placed between the reference and the working electrodes, talked about that, and this voltage initiates an electrochemical oxidation reduction. And then you measure the resulting current as a quantitative indicator of the analyte's concentration. And the Cottrell's equation is shown down here, and the parameters are shown below. And again, this happens to be a very convenient way to take the parameters of the sensor, roll them up into an equation in order to be able to compute the current output. So interesting, yeah, this is a simplification, but the simplification involved some assumptions. Sensors are very complicated in many different ways, but the derivation of this equation is based on a theoretical flat plate surface. And therefore, that's not necessarily realistic for a lot of our electrodes. And of course, this assumption is the so-called planar macro electrode. So what happens is that, let's consider for a minute that the sensor is energized at t equal to 0, and factors, and all other factors being same, the current will diminish over time and not reach a steady state. All right? The key is to recognize that the electrode surface is continuously refreshed due to the migration of reaction products away from the electrode. Remember that diagram where we showed the reaction occurring and then the flow of analytes. So it's a continuous process, continuously refreshed surface due to the migration of reaction products away from the electrode. And of course, it's not static, it's dynamic, and that is the origin of your current that you'll be measuring. An important aspect of sensor performance is the mass transport. Mass transport, as we mentioned, refreshes the analytes on the electrode surface that then become available for reaction. And mass transport, the patterns depend on a lot of different things and actually can depend on the electrode dimensions. So we'll talk about that in just a second. But essentially, repeating what we've just commented on, the transport of mass to and from the electrode is an important role in the progress of the reaction of the electrode. And this is important. If the rate of transport of reactant to an electrode is slower or comparable to the rate at which the reaction occurs at the electrode surface, then mass transport plays a significant role. Once again, if the mass transport of reactant to the electrode is slower or comparable to the rate at which the reaction occurs at the electrode surface, then this is mass transport limited, and we need to explore the forms of mass transport and influence them if necessary. And so we have three different types of mass transport. Many of you would know this from your fluid dynamics course: diffusion, convection, and migration. Diffusion is something we're probably all really familiar with, but really arises from local uneven concentrations of reagents. And so basically what happens is that the diffusion is particularly significant in an electrochemical experiment, since the conversion reaction occurs only at the electrode surface. Consequently, think about this, there's a lower reactant concentration at the electrode than in the bulk solution. So what does this mean? We have diffusion from the bulk solution to the electrode surface. Similarly, a higher concentration of product will exist near the electrode than further out into the solution. Right? So again, the concentration of the product exists near the electrode as opposed to being further out into the solution. So you see that effect of diffusion on this, on the concentration. Another mechanism of mass transport is convection. And convection results from the action of force on the solution. It can be a pump, flow of gas, or even gravity. So there's two types of convection that I think many of you would be familiar with, but one is natural convection. And natural convection is actually present in any solution because it's generated by small thermal density differences. And they kind of act to mix the solution random and actually in an unpredictable manner. So in the case of electrochemical measurements, these effects tend to cause problems if the measurement time for the experiment exceeds 20 seconds. So this is a time-dependent process. It's possible to drown out the natural convection effects from the electrochemical experiment by deliberately introducing convection into the cell. This form of convection, forced convection, is called forced convection. It is typically several orders of magnitude greater than any natural convection effects and therefore effectively removes the random aspect of the experimental measurements. So basically, what we're saying is that in the case of mass transport, speaking of convection and diffusion, diffusion is just going to be there anyway, but you can swap out that effect with convection. Kind of a balancing act, but basically the random aspects of the measurements you just want to kind of avoid, and the convection may be a forceful way to do that. The final form of mass transport we need to consider is migration. This is essentially an electrostatic effect in which arises due to the application of a voltage on the electrodes. This effectively creates a charged interface, the electrodes. Any charged species near the interface will either be attracted or repelled by electrostatic forces. The migratory flux induced can be described mathematically in one dimension using the equation on the right. Phi is the potential across the interface. However, due to ion solvation effects and diffuse layer interactions in solution, migration is notoriously difficult to calculate accurately for real solutions. Consequently, most volumetric measurements are performed in solutions which contain a background electrolyte. This material is a salt that does not undergo electrolysis itself, but helps to shield the reactants from migratory effects. The purpose of introducing a background electrolyte into a solution is not, however, solely to remove migration effects, as it also acts as a conductor to help the passage of current through the solution. So this is a case where migration is a real issue, and you introduce the conductor, but it has multiple purposes. One, it can reduce migration, but it can also obviously facilitate the passage of current through the solution, and that's one of the things we'll be measuring. As I mentioned a couple slides ago, these calculations and the characterization of the phenomena, they really are a function of geometry. So we talked before about that planar assumption. Sometimes people use different configurations, and one of them that seems to be popular is what we call the micro-disc electrode. So we have a disc of radius r, and then the steady-state diffusion-controlled current is given by this equation, where Re is the radius of the microdisc electrode, N is the number of electrons transferred, F is the Faraday constant, and dx is the diffusion coefficient of x. So a lot of different parameters to put in here, but the idea is that if the sensor is placed with a restricted diffusion space, again, restricted diffusion space, the bulk term is dropped and the geometry is given by the aspect ratio. Kind of a convenient thing. To summarize, the last slide really brought out one of the many aspects of amperometric transducers that are possible to discuss. Geometry. Do you make a planar assumption? Is it a disk? Can you ignore bulk effects? What is it doing for migration? What kind of diffusion do you have? Is it natural convection, forced convection, classic diffusion? And so hopefully that wasn't too overwhelming. And really what we wanted to do was just provide just a comprehensive exploration of the sensors and only dive briefly into various key elements such as the three-electrode system, enzyme-mediated reactions, and of course what we focused a little bit more earlier in the part 1 of this was the critical application of the amperometric sensor in glucose measurement. Hopefully, a lot of topics here, a lot of different things. Hopefully you gained some insight into the fundamental principles, the mechanisms, and a few of the practical considerations really essential for understanding and implementing amperometric sensor technology.